Parent function set number 1. Cubic, cube root, quadratic, square root, and absolute value. So we're going to talk about the attributes, the characteristics of all 5 of these parent functions. There are more, but this is just the first set because these have a lot in common. So let's first talk about the cubic parent function. So for the cubic parent function, the equation is f of x is equal to x to the third power. That's how you recognize a cubic function from the equation. As long as it has a third power, it is in the family of cubic functions. The reason these are called parent functions is because these have no transformations done to them. They're not shifted left, right, up, or down. They have no compression or stretch vertically or horizontally. So these are the original functions. These are the ones that are the simplest version of themselves. So for cubics, it is just simply x to the third power. If the highest exponent you have in some equation is a third power, then we know that is a cubic function. So now let's talk about the domain of a cubic function. You can memorize this, but you can also just figure it out by remembering what the graph looks like. So for the graph of a cubic, we have this arrow here pointing down, but it also points left. So far my domain is negative infinity. Then furthest to the right is this arrow, which points right forever. So that means positive infinity over here. So the domain of these cubic functions is negative infinity to positive infinity. That means all of their x values can be basically any x you want. I'm allowed to have every single x into this function. Now let's look at the range. The range is okay, well, if I can have all the x's, all the inputs, what are all the possible outputs that I can get? So this arrow, again, the furthest down is negative infinity, and the furthest up is again this arrow at positive infinity. So we have this for our range. So because I can use every single input, that means I can also get every single possible output, every y value. So the domain is all real numbers and the range is all real numbers as well. Now, the x and y intercepts. So this function crosses the x-axis at the coordinate 0, 0. It crosses at the origin. And since it crosses at the origin, that means the y-intercept is also at 0, 0, also at the origin. So this has an x-intercept and a y-intercept of 0, 0. Now, there is some symmetry with this function. We're used to being able to just draw a line down the middle and have it be the same on the left and the right. Well, for a cubic function, this actually has rotational symmetry. What that means is that means that I can take this piece here, and if I rotate it, I get this piece here. So that's what rotational symmetry means. I can take this section of the graph, rotate it over, and I end up with this part. So this isn't symmetrical about any line, it has rotational symmetry. Those are some characteristics to memorize about the cubic function. Now let's talk about coming up with a table of values. So with these table of values, you can basically pick whatever you want. Remember that the x's are the inputs. This was that domain that we talked about earlier. And if I look at the domain from earlier, I can have any value between negative infinity to infinity. I can take any x that I want. Well, let's take some x's that make sense. I don't want to have too far negative. I don't want to have too large of positive numbers. And I also want some on the negative end and some on the positive end. Let's get a little bit of both. So I'm going to choose an x value of negative 2. I'm going to start there. Now, to find the output, we're going to take that negative 2 and plug it into the equation up top. So the equation was f of x equals x to the third power. So we're going to do f of x equals x to the third, but the x that I have is negative 2 to the third power. So negative 2 to the third power means negative 2 times negative 2 times negative 2. So you're multiplying it by itself 3 times. So negative 2 times negative 2 times negative 2 comes out to be a negative 8. So that is the output that goes with the input of x. This part of the table is not usually shown. Usually you just have an x and a y, but I thought for your notes this would be important to have so you can see how we're coming up with this value on the right. Now, another good x would be negative 1 because I'm allowed to have negative 1, and cubing negative 1 is very easy to do. So f of x equals, again, we're going to take our x, which is negative 1, to the third. And that means -1 times -1 times -1, which makes another -1. Then our next would be a 0, because that's what comes next after -1. So we have f of x equals 0 to the third. Well, 0 to the third is 0 times 0 times 0. So 0 to the third just makes, well, 0. That's all it makes. So now let's try our next one. 1 would probably be the next logical number. So we have f of x equals, we're going to take 1 and cube it this time. Our x value is a 1. So now we have +1 to the third. So +1 times +1 times +1 equals 1. 1 times 1 times 1. And then our last value is going to be a 2. So we have f of x equals 2 to the third power. And again, this is a +2 now. So 2 times 2 times 2 comes out as a +8. Okay? Now, you could have technically picked any x value you wanted. Because the domain is -infinity to infinity, these x values can be anything. I could have chosen -800 if I wanted to, but I wanted something that I knew would fit on the graphs that I'm given for most things. So -2 to 2 fits on the x here's -2 to 2. And then -8 to 8, well, that doesn't quite fit on this graph, but it fits most graphs. So this is how we end up with the table of values for the cubic function. We have to remember that the domain is all real numbers, so I can pick any x's that I want. Now, let's talk about the function that's related to the cubic. Let's talk about the cube root. So these two are actually inverses of each other. That's why they look very, very similar. So the equation of the cube root will be f of x equals the cube root of x. Now, when you're drawing the cube root, make sure this is a small number inside the crook of the radical. You should know that word from Algebra 1. The index tells you what kind of root you have. So this is a cube root of x. Now let's look at domain. So domain is, we have this going to -infinity. And on the right, we also have another arrow also going to +infinity. So just like it's almost twin, it also has a domain of all real numbers, -infinity to infinity. And the range, this arrow is slightly pointing down. It's not very quick, but it's slightly pointing down to -infinity. And same over here. This one's slightly pointing up. It's not very quick, but it is pointing up to +infinity. So for our range, we also have all real numbers. All possible inputs, all possible outputs. Let's talk intercepts. So if we look at our graph, this also crosses at the origin at 0, 0. So that means the x-intercept and the y-intercept are the same. Now, since this is very similar to the cube function, this also has rotational symmetry. I can take this piece here, rotate it, and I end up with this piece. So this also has rotational symmetry. Now let's talk about the table of values. So again, since the domain is all real numbers, I can pick any x's that I want. But let's be strategic about this. So a cube root means I'm undoing cubes. So I'm kind of starting here and working backwards. I'm undoing things that are cubes. So if I tried to pick a 2, for example, if I tried to find the cube root of 2, well, what I'm looking for then is what times itself 3 times gives me a 2. And there's nothing. The first nice cube that I have is actually 8. In this case, we would be using -8. So the process here, the f of x equals the cube root of my x, which in this case is -8. So I have to ask myself, what times itself 3 times gives me a -8? Well, I know 2 times 2 times 2 is +8. Well, what if I did -2 times -2 times -2? This is +4 times -2 makes -8. So the output would be a -2. If I take -2 and multiply it to itself 3 times, you end up with -8. So the cube root of -8 is -2. Cubes make numbers larger. Cube roots make numbers smaller. So the next perfect cube is what we call it, just like perfect squares. The perfect cube would be -1. That'd be the next perfect cube. So since I know I have to take the cube root, I'm choosing numbers. I'm choosing x values that I know are nice, perfect cubes. They're not going to give me crazy decimals. So the cube root of -1, well, let's see, what times itself 3 times makes -1? -1 times -1 times -1. So the output is a -1. The cube root of -1 undoes itself into a -1. Now let's plug in a 0 because that's the next perfect cube. F of x is equal to the cube root of 0. And again, what times itself 3 times is a 0? Well, that has to be 0. 0 times 0 times 0 makes a 0 on the inside. The next perfect cube would be a 1, positive this time. So we're going to do f of x equals the cube root of a positive 1. So what times itself 3 times is a 1? Well, that'd be a 1. 1 times 1 times 1. And then the final perfect cube is 8. So your f of x equals the cube root of 8. So what times itself 3 times is going to give us an 8. We've kind of already answered that. 2 times 2 times 2 makes 8. So that means the cube root of 8 is equal to 2. And this is the table for the cubic parent function. This is not something you have to memorize. Sorry, this is the table for the cube root parent function. You do not have to memorize this. These are numbers that you can choose yourself. I can choose any number I want. I could have even technically chose a 2. But if I try to take the cube root of 2, you end up with a decimal over here, and decimals are not easy to plot on a grid, which is why I didn't choose 2 as an input value. Okay, so just be mindful of the numbers you're choosing. Okay, let's move on. Quadratic parent function and the square root parent function. This one you should have seen the quadratic from last year. So your equation for this is f of x equals x squared. And that's how you know you have a quadratic. If your highest exponent is a 2, that is a quadratic function. So the domain of these, well, let's see. This arrow means I'm going left forever, so this would be -infinity. This arrow is moving right forever, so that would be positive infinity. So my domain is again all real numbers. I can have any number from -infinity all the way to positive infinity. But if we look at range, this stops at 0. So my lowest point is 0, and my highest point is going to be infinity. So I don't have all real numbers this time. I have 0 with a bracket because 0 is included, and then I go to infinity. Okay, now let's look at x-intercept and y-intercept. So the x-intercept is sitting here at 0, 0, starts at the origin. A lot of parent functions do. Not all of them, but a lot of them do start at the origin. And then the symmetry for this one is the y-axis. This is symmetrical about the y-axis. So what that means is if I were to draw a line right here down the middle, I could fold this entire parent function over that line, and I would end up with a match on both sides. This is symmetrical over the y-axis. Now let's talk about the table. So we're going to choose x's, and we're going to find out our y's, our outputs. Well, the domain says I'm allowed to have all real numbers. So I can have negatives, I can have positives. I can even have fractions if I wanted. But again, fractions are hard to graph. So I'm going to choose nice, pretty whole numbers, some negative, some positive. So I'm going to stick to the -2 again, the -1, the 0, 1, 2, and I guess 3. Okay, so let's plug these in. I need to figure out how to find my y's. So we have f of x is equal to x squared. So I'm going to take x and square it. So when I square a -2, look what happens. Squaring a -2 means -2 times itself. Well, if I do negative times a negative, I get a positive number. And 2 times 2 makes 4. Okay, that kind of makes sense so far. It's not supposed to be negative because my range says I'm allowed to have every y value as long as it's above 0. And so far, we're above 0. Now let's try the next one. If I plug in f of x is equal to, and I'm going to take -1 and square it this time. Oopsie, blue. I'm going to take -1 and square. So if I do -1 times -1, well, again, a negative times a negative is a positive, and 1 times 1 makes 1. So if I take f of x and I square 0, well, that means I'm going to do 0 times 0, which is 0. And now look what happens if I square 1. So now I'm going to take f of x equals 1 and square it. Well, 1 times 1 is 1. So look what happened. Look at your y values. You were started at a high y value, a positive. You went lower, and then you jumped back up. You didn't get to the negatives. You stopped right at 0, which is exactly what this graph shows you. I can have the high y values. I come down. I'm going to stop at 0 and then go back up. You don't have negatives. And it makes sense because if you square negatives, you're going to have a negative times a negative, which results into a positive. So it makes sense that I'm not allowed to have negative values for the quadratic parent function. So let's continue. So now we're going to do f of x equals 2 squared. Well, 2 squared means 2 times 2. So that'll give us a 4. And then we have the last one, f of x equals 3 squared, which will give us 3 times 3, which makes 9. And also, let's look at symmetry. So for the symmetry, here we go. For the symmetry of this graph, it's supposed to be along the y-axis. Well, look at your y's. They're symmetrical. 4, 1, 0, 1, 4. They start repeating after you hit 0. This shows the symmetry that my graph does as well. It's symmetrical here and here. So the graph and the values should all make sense with each other. They should go together, okay? Now let's look at the square root. So just like the cubic and the cube root were inverses of each other, the quadratic and the square root are also inverses. So the equation of the square root parent function is f of x is equal to the square root of x. So it looks similar to the cube root, but we don't have an index. So let's review from last year. If there is no number here in the crook, we know it's a 2, it's a square root. Let's look at domain and range. So here's the graph. Here's what it looks like. This is something you need to memorize as well. So it starts here at 0, and it goes on forever. So this is one of the functions that is not in all real numbers for its domain. It starts at 0 inclusive. It includes 0. It's a solid point, and it goes on to infinity. So this means I am not allowed to have any negative x's. I can start at 0. 0 is okay, but I can't have -1. That's not going to work in this function. So for the range, it again starts at 0 and goes up to infinity because this arrow here is going upwards just slightly. So on my range, again, I can have 0 and I go to infinity. I'm not allowed to have negative ranges either. So these are very similar, domain and range. So the x-intercept, just like the rest of these, was 0, 0. And the y-intercept as well. It starts here at the origin. The symmetry on this one, well, all I have is this one little piece. There isn't any. There's nothing I can do to try to make that guy symmetrical in 2 pieces. There's nothing that I can do. So the square root function does not have any kind of a symmetry to it. So let's look at the table of values. So on all of the previous functions, I've used negative numbers to start the table. But according to my domain, I'm not allowed to have negative numbers. So I need to start, my lowest I'm allowed to start at is 0. So I need to put a 0 here. And then I can go up from there. Well, let's just do 0, and then we'll continue with the rest. So the process is f of x is equal to the square root of 0. So I need to figure out what times itself, because that's what a square root does. A square root asks what times itself will give me a 0. That's what a square root does. Well, 0 times 0 is what makes 0. Now, the next logical number is going to be a 1 for this one. And here's why. If I do f of x equals the square root of 1, my question is, what times itself is equal to 1? Well, 1. 1 times 1 makes 1, so that works. The next logical number is not a 2 because there is no number times itself that gives me a 2. The next one is a 4. So if I look at 4, and here's why I picked 4 and not 3. So if I try to do the square root of 4, well, what times itself gives me a 4? Well, that's 2. 2 times 2 makes 4. These are all perfect squares. So the next logical x is not a 5, it's not a 6, it's not even a 7. The next logical number would be a 9 because that's the next perfect square. F of x equals the square root of 9. Well, what times itself gives me 9? That would be a 3. That would be a 3. 3 times 3 makes 9. 3 times 3 makes 9. And that's how we know that that's a perfect square. So the next logical one would be 16 because I know that if I do 4 times 4, I'm going to get a 16. So the square root of 16 is also a nice, pretty whole number. And the last one for this table would have to be 25. I could continue this table on forever and ever and ever. Okay, but we're not going to do that because remember, the domain is 0 to infinity, and we're not going to continue this table forever. The square root of 25 is 5. 5 times 5 is 25. Now, that doesn't mean I cannot use values like square root of 2. I can, but the square root of 2 is like 1.41 something, okay? And this isn't very easy to graph, which is why I didn't choose an input value of 2. I chose input values that would make whole outputs, okay? Last one. Let's talk about the absolute value parent function. So the absolute value looks extremely similar to a quadratic, except that it has a point at the bottom and not a curve. Okay, so the absolute value parent function is the equation f of x equals, and this is called the absolute value of x. That's how you read that. These two vertical bars around x means the absolute value of x. That's how you read this. Let's look at domain. So my domain is the furthest left to the furthest right. Well, this guy goes left forever. So that's going to be negative infinity. And he also moves right forever, which is positive infinity. So the domain of the absolute value is all real numbers. I can have any negative and any positive, including 0. I can have 0 too. I can have 0 as well. Let's look at the range. Well, it V'd right here, right on the origin at 0, 0. So that's my lowest y value possible. There is no negative y's. Then the highest it goes, this arrow moves up. This arrow also goes up. So that means the highest is going to be infinity. So my range is 0 to infinity. Now, the x-intercept, just like the rest of these, the x and the y-intercept are starting at the origin of 0, 0. That's why these all are on the same page. They're in the same set because they're extremely similar to each other. And there is symmetry for this one. I can take this side and fold it over, and I end up with the other side. So there's symmetry across this y-axis, just like the quadratic. There's symmetry across the y-axis. Now, let's talk about the table of this guy. So since I have a domain of all real numbers, that means my x's can be anything. So I'm going to go back to my -2, -1, 0, 1, and 2. I'm not going to use this last part of the table. So -2, -1, 0, 1, and 2. Those are all good x values because they're all in the domain. They're all in this guy. Now let's talk process. When I do f of x equals the absolute value of -2, absolute value takes negatives and turns them positive. That's what it does. So if I have the absolute value of -2, the output is a +2. For the next one, f of x equals the absolute value of -1. So again, it takes negatives and makes them positive. So the output would be a +1. It doesn't multiply, it doesn't do anything like that. It just takes the negatives and makes them positive. So if I do an absolute value of 0, well, 0 is neither negative or positive, so it's just going to pop back out as 0. It's right in the center. It's just going to pop back out as 0. And then if I do the absolute value of 1, well, 1 is already positive, and it doesn't turn positives into negatives. That's kind of backwards from what I did earlier. So if it's already positive on the inside, it just stays the same number. So the absolute value of 1 is equal to 1. And then that means the same for this guy. The absolute value of 2 is going to produce a 2. So it takes negatives and turns them positive. And if they're already positive, it just stays the same number. So things you need to memorize. Things you need to memorize. Write this somewhere down. We need to memorize the way the graph looks, the equation, and that's pretty much all you need to memorize, because domain and range you can figure out from the graph. The symmetry you can figure out from the graph. The table you can figure out from the equation, and also the domain and range. Okay, so these are really the only 2 things you need to memorize. I need to be able to match up the graphs to the equations and see what they look like, because you can always sketch a graph. I can always come over here and sketch a quadratic, or I can come over here and sketch an absolute value. That's not a problem, but it's memorizing the graphs with their equations and their names. Ooh, that's a good one. Don't forget their names. Hello. So graphs, equations, names. Those are the things you need to memorize, and you need to memorize them as groups of things. Now, down here, label the following as cubic, cube root, quadratic, square root, absolute value, or none of the above. So we're going to use these graphs. These are not the parent functions, but they are families of functions. So just by knowing the graph, we're going to identify if this is a cubic, cube root, quadratic, square root, or absolute value. So I like the easy ones first. Number 2 is a quadratic, because if you look at your quadratic graph, it was that U shape. That's how you recognize a quadratic. It has that U shape here. So the number 2, we can label quadratic. Now look at number 1. This is like an S. It's a sideways S. Well, that is what an S is. So if you look at number 1, absolute value is a V. Quadratic is a U. The square root is like a portion of a U sideways. Let's see. Cubic starts at the bottom up, like it's a vertical S. And then cube root is an actual S. It's sideways. So if I look at number 1, this is that sideways S. So this models the same direction as a cube root function. So this is in the same family as the cube root parent function. Now, number 3 is an L shape. This does not model any of the functions we have currently talked about. So this would be none of the above for now. Now 4 has the vertical S shape. That's your cubic. It's not the parent function, but this is in the same family as the cubic parent function. Number 5 is also none of the above. This is a line. This is that linear function we talked about. So it's none of the above. 6, that's your sideways U that only has a portion of it. So that's your square root. Again, it's not the parent, it's a part of its family. So these are all together. This is a square root function just like the parent. Now, number 7 is that U shape. Yes, it's upside down, but it's still a U. This is quadratic. Now, number 8 is a V shape because it points at the bottom. It doesn't curve at the bottom, so this is an absolute value. All right, so 9 through 16, pause the video and see if you can match them with their correct families of functions. And these are your solutions. So we need to work on memorizing the name of the function, what its graph looks like, and its equation. Everything else you can figure out from one of these 3 things. So we need to work on memorizing these for this current set of functions that we have.